I hope you can hear me. Oh, hi there. My name is Ryan. I'm lead developer at face.com. It's a pretty big dating site, quite popular in Russia. We have apps in major social networks, including Facebook. We also have a standalone version and mobile applications. Well, you can give it a try if you find my talk very boring. This is our main numbers. We have 60 million users and more than 100 million photos. And because we're a dating site, photos are very popular for us and important, so we show them a lot. It's at least 16 photos on main page and up to 200 feet. Usually they are small photos, so that's a lot. So this is talk about photos, as you may already guessed, but there will be no photos on slides and also no JavaScript. So let's look at some more numbers to warm up interest to this topic. So we have 12 storage nodes, all bare metal. They hold 70 terabytes of data, but only 44 terabytes actually used. When we keep original uploaded photos, we don't keep resized version. We resize on the fly and keep in caches. More about it later. This is our traffic. We transfer as much as internet transferred in total in 1994. That's not very impressive these days, but that's some kind of comparison. We also tried using CDN, but we had bad story, so I won't tell you. And that's basically the reason I'm here, because we did it using open source and node.js in particular. And I'd like to share what came up. This talk is in 3 parts. I hope we can make it in 20 minutes. First part is about architecture. I'll show you what's happening when you send a request to get some photo. So this is a very basic view of our infrastructure. HTTP request hit front ends, also known as balancers, that route request to cache servers. If cache miss occurs, cache servers ask resize server, and resize takes data from storage itself and gives what you wanted. Of course, there are front ends. Usually, you want to keep more than one server to survive failures. So we have more than one of every kind of server to eliminate single point of failure. Okay. We use Nginx as HTTP server for everything, and photo storage front ends isn't an exception. Nginx is very fast, predictable, and reliable for us, so we love it. We use it everywhere. And this model, upstream hash, will help you to route request to caches. So basically, it hashes incoming URL to some kind of number, and then divided number and route request to appropriate server. If some server is dead, we'll just skip it and route to another server. So here comes a pretty straightforward tip, but that's very important. Don't cache anything twice. If you have many servers for caching and you don't use hashing, you may end up with a pretty weird situation where you cache files more than on one server. So let's look at this. So this is how you shouldn't do. In this example, you can see 3 different cache servers and 3 different files. And because we didn't use any clever routing, we ended up with 9 files, but only 3 are unique. And also we sent 3 times more requests to backend, so that's not very good. So this is how it should be. We used the same 3 servers, but we hashed each file to only one server. And if you request file number 2, you only hit the cache server number 3. Okay, that's simple and elegant. But if cache number 3 is dead, hashing will route request to some other server, and it will cache the file. So when we started making photo storage, we didn't have SSD, so we cached data in TMPFS. Maybe we did something wrong. Maybe it's TMPFS itself, but it was horrible because for some reason, at some point of time, system decides to remove the whole TMPFS to swap, and this is totally irresponsible. So we now use SSD and happy with this. And also, SSD isn't that expensive if you want some kind of caching for that kind of data. Not for very hot data, but like moderate hit data. So, okay. And also, if you're afraid of disabling trim, don't be. We're absolutely good without it. And here comes another tip: overallocate caches. What I mean here, if you have today, if you have 4 cache servers, and tomorrow you may have 5 or 6, you better divide them into like 20 virtual servers. So if you want to add fifths, you just take one virtual server from each physical and move it to a new one. And this way you'll see no downtime, and no cache misses will be at the same level. Nothing would change. So we do resize it on the fly. It saves us disk space, but it's not the reason. It gives us flexibility to add new photo sizes. We already dropped a couple, and as I know, we added 3, and without disk capacity changes at all. So if you have not so much CPU, you may decide to save resized photos on disk, but actually this is not the case we want. So here we use Nginx again with image filter model. We patched it for us, and even some patches already in Nginx. We also have patch and review to crop photos. And okay, never mind. You can find it. So that's all about Nginx. Let's move to an actual storage part. This part is about Backpack, our storage solution for immutable data. Well, first try was Nginx 2. We didn't think about writing everything, so we tried Nginx. If it's so cool, why not try? It was okay for 1,000 files, and it even was okay for 10,000 files, and even for 20,000 files. But when we hit page cache limit, it became totally irresponsible. For those of you who don't know what's page cache, it's like your disk mapped to a fast memory. So if you read something twice in a short period of time, you're probably going to hit page cache and read from memory instead of disk. And if you change data, you probably change it in page cache before flushing to disk. So if page fault occurs when you miss this cache, you're going to hit the disk. So this is very bad, especially if you don't use SSD and use mechanical disk. So this is why it's so bad, because of random access. Mechanical disks are spinning, so that's not like SSD. You cannot jump between blocks. You should spin this disk and move the head to appropriate position, so that's not that simple. And we cannot predict what photo user will ask, so we just put them on disk, and then we decide how to read it. So that's disks are spreading. So that's the problem. Unfortunately, SSD isn't that cheap these days, and it was even more expensive when we started this project. So we use usual mechanical disks for actual data storage. So mechanical disks are pretty cool if you need to linearly read data. If you have a file that is 10 gigabytes, you just can read it at 200 megabytes per second. But if you want to read 10,000 small files, you are in trouble. So, okay. Node.js to the rescue, because, you know, Node.js is event-driven IO something. And Redis. And probably Zookeeper if you plan to use many machines and care about availability, and we do. The simple idea, we just don't seek more than needed. And just don't do anything you don't need. You probably don't care about metadata if you store millions of photos. So you don't care about permissions, you don't care about creation date. You can save it somewhere else in fast storage. So we're not pioneers in this. This idea is inspired by Haystack. This is photo storage for Facebook. There's a white paper, Finding Needle in Haystack, where guys from Facebook describe how it works. Unfortunately, this system isn't open source, so we have to write it for us. So the first idea is to concatenate small files into bigger ones. So this way you just avoid disk movements for information you don't need, like permissions. So if you think for a moment, this is a quite common pattern in usual databases like MySQL. MySQL doesn't save each row in separate file. It has just big chunks of data, and you know, this way databases kind of reinvent file system to achieve performance. So we'll do the same. So, and the other idea is to always keep index in memory. Index is usually much smaller than actual data, so you only need to hold name and few extra bytes. So we can afford that. This way we don't have to use disk to figure out if we have some file or not. And if you know that we have some file, we can read it in one syscall. So the realization on disk. We can separate the whole realization in on-disk realization and in memory. I'll describe how it works on disk. We have 3.5 gigabyte files. Each one holds like thousands of photos usually. And we have as many as we can fit in one disk. The number 3.5 gigabytes, because this is smaller than 32 bytes unsigned integer, I guess. Well, this gives us some benefits if we want to save this number in memory index. Basically, you just append each chunk of data to these big files, and that's it. You're done. So, but we can't use these files just like standalone unit of data. So we have index for each file, and that's what's inside. We have name of our data, of like actual photo name, of set in big file, and length of our data. This is with this index, each big file has like own meaning. But this is not to use like in-memory index. This is just to repair if Redis, I don't know, crashed and database is corrupt. Let's talk about realization in memory. We use Redis in append-only file mode to write to disk as fast as we can. In Redis, we keep keys for each file, for actual chunk of data. For hero name is actual photo name. We map file name to file number, big file number, offset, and length. So this way, we can look up in Redis for each photo very fast. That's how it looks all together. We have in-memory Redis database, and on disk we have many big files and fallback indexes. And it's all managed by node.js process. From the outside, it looks almost like WebDAV. So we can do get and put, but that's actually enough for photo storage. We really don't want to delete any data. And, well, also, this way, React looks like WebDAV too, and probably Elasticsearch types the same. This is how put request happens. We write data to big data files, write to our index on disk, and we write Redis key, and then we return success to client. So subsequent GET request can read Redis key from memory without any disk involved, and can read data from disk with single syscall, like I guess pread. And we keep all data files always open, so we don't have to open them again for each request. And this is like comparison with Nginx. We saved 2 million files on disk, each like 10 to 50 kilobytes, and read 10,000 files. Here you may see blue is Backpack and red is Nginx. As you may see, Backpack performance was pretty stable because we don't depend on page cache. But Nginx was like increasing, but in the end you see, I guess that was increasing page faults, so performance decreased. And we also finished 33% earlier. So lesson here is less disk 6 lead to bigger throughput. And what you actually should learn from this is you should know your bottleneck. In our case, that was disk. And as a bonus for Backpack, we have linearized access for processing. You have these big data files. You can read the whole index and then like read the whole big file and emit, I guess you may emit events for each found photo. Okay. And this part is about management. Well, single Backpack node knows nothing about external loads, so we have to combine them in cluster that can actually survive server failures. This is kind of list of tasks. What I mean when I say management, first of all, you need to add servers to extend capacity, then you need replication, and then you need failover, because we have to use it in production. So we use coordinator. It's a node, not Node.js, just usual node that doesn't hold any data, but it knows everything about the cluster. Normally you do put request on coordinator, and it says where it put the data. It also coordinator combines servers into shards. Dominic told you about shards. So basically, shard is just a bunch of servers that hold the same data. And that's why we need Zookeeper. Zookeeper is coordination service. I guess Hadoop uses it. Sometimes people use it with Elasticsearch. Here, we at Topface use it for config files distribution and I guess for something else. Personally, I don't like Zookeeper, so maybe we'll replace it with something better. So the first try was DHT, like Amazon Dynamo, because you know all the cool kids do this. So, but no, that was a bad idea because of rebalancing on capacity change. When you add a new server, you have to split hash ring again, and you have to move data around. But we don't need this. We did a good job avoiding extra work in single backpack instance, so we don't want to do extra job here. So, no, we tried it, and actually we failed because of data movement. On the last capacity upgrade, we've seen like 10 gigabits per second for straight 8 hours. Well, maybe it's not that much, but it was scary. Okay, so we tried to make it simple. Simple things are easier to maintain, and some developers are people too, and have feelings, you know. So what do we mean here? We want to avoid rebalancing, so we'll use primitive sharding. So this idea has its limitations because we need to save shard number, but we can afford a couple of extra bytes. So here you may see 2 shards with 3 instances in each, and 2 images in each, 1 image in each shard. And they have 50% used capacity, so probably that's a big images. So if you want to retrieve LOL JPEG, you can't just use every shard and every node. That's the number before actual file name that gives you the shard number. And you can ask this file on any node of this shard. So basically, when user uploads files, we generate photo name, and then we upload that photo through coordinator and get this number, like 1 in this case. And we save actual photo name and shard name in like single string to retrieve this later. And you probably notice empty space on the right. So let's set 1 more shard. This shard is empty, so it has 50% chance to save new photos. So like if you want to save the next photo, you have 50% chance to save it on this shard. And eventually, every shard will have the same used capacity. So coordinator actually knows how to handle the next files this way. And there's no rebalancing. It's simple. Let's talk about replication. I mentioned this as one of management tasks. Let's look how it works for Backpack. That's the question we ask when we start doing something. What if meteorite will hit your node? We call it meteorite-driven development because we don't want downtime. We want to work even if some nodes are like crashed with meteorite. So replicator is a node that actually moves data around. You have to make multi-node shards to take advantage of replicator. If you have just 1 node in shard, you don't need to replicate anything. Replication works inside of shards. So if you have three nodes in 1 shard, you actually save to 1 node and then replicate to other nodes. So, and you have to distribute shards across servers, because if you don't, meteorite will just bring the whole shard down. That's not what you want. So that's the simple picture of how it works. If you want to save an image, coordinator does that on one server and tells our replicator to replicate that photo to make it available on every node. And this happens like eventually. Maybe it won't happen, but we hope it will. Because if some node is down, we just keep a message like copy that file to this node in queue, and when node is alive again, we'll do what we should do. And the whole thing is bulletproof if you need it. But if you don't, like in staging environment, you can run everything on one node. Nothing will complain. This is like if minimum, I don't know what to say. This is if you have 3 servers, you can make it available if one server is dead. So if you have 3 zookeepers, this cluster can survive 1 dead zookeeper. Backpack actually don't care about anything. Coordinator nodes are all the same. Replicator nodes are all the same. So this way you can survive 1 server. If you have more servers, then you can survive more dead servers. So as I promised, this is open source. You can find it on GitHub or install from NPM. Well, that's it. Thank you.